trig integrals. So of course we have our standard integrals that we already know. So sine goes to minus cos, cos goes to sine, sec squared goes to tan, and whilst tan's not a standard one, of course we can write it as sine on cos, and it becomes minus the log of cos or the log of sec, whichever you prefer. So they're our standard ones. What about if it's sine to the power of something or cos to the power? Now, I'm just going to work through the sine to the powers because cosine is a complementary ratio, so the technique's exactly the same for cosine. So sine to the power of 1, well, then we've got our standard integral, so minus cos. Sine to the power of 2, well, we know we can rewrite sine squared as a half of 1 minus cos 2x, and then integrate that, so we get half x minus half sine 2x. Okay, so now we come to cubed. So with the cube, what we do is we split it up into sine x times sine squared. Now the reason we do that is the sine squared I can rewrite as 1 minus cos squared. And now I can do it via a substitution. Because if I make u equal cos x, the u is minus sine x dx. So I can rewrite that as minus the integral of 1 minus u squared. And well, that gets a third u cubed minus u, which becomes a third cos cubed minus cos. And basically that idea will do with any odd power. Because if I have an odd power, I can always factorise out the sine x. That will leave me with sine to an even power inside. Well, an even power I can always write as sine squared to the power of something. The sine squared I can always change to 1 minus cos squared, and then I do the substitution u equals cos x. What about sine to the power of 4? This one I'll deal with a little bit differently. This time I'm not going to pull out the sine x, because that would leave me with an odd power. And so, well, it's all right. I suppose I could write it as sine squared to the power of some fraction. That's going to be a bit hard to expand out when I get 1 minus cos squared. So it's easier this time to write it as sine squared squared. The sine squared I then change to a half of 1 minus cos 2x. But I'm squaring it in this case, so I get a quarter rather than a half squared. The cos 2x, or the 1 minus cos 2x, I can expand out. And now I have 3 different ones to deal with. The 1's okay. The cos 2x is okay, but the cos squared 2x, now I have to use my technique for cos squared, and so that'll become a half of 1 plus cos 4x, tidying all that up, a quarter, 3 on 2 minus 2 cos 2x plus a half cos 4x. I've now got something I can integrate completely. So I end up with a quarter outside of 3 on 2x minus sine 2x plus an 8 sine 4x. So when it's an even power, I can always rewrite that one as sine squared to some power. And this time for sine squared, I'm not going to substitute in 1 minus cos squared, but I'm going to use the double angle result. So I'll substitute in the half of 1 minus cos 2x. Now this, depending on how high the power is, of course, will always end up meaning more work to do than the odd power. So you're always keeping your fingers crossed. I want an odd power. Okay, so odd, just to show you, well, if I keep going, odd's so much easier because you can just pull out the sine x, the sine squared you can change to 1 minus cos squared, and bang, now you can do your substitution. U equals cos x. And all right, you still have to expand out something, but that's, I think, a lot easier to expand than the other ones. Integrate, sub back in. So that's if we just have sine to the power of something. And as I say, you'd use the same technique for cosine. What if you got both? So now we've got sine to the power of n and cosine to the power of n. Now most of the time you're just going to do this via a substitution. U equals sine x or u equals cos x. So rather than starting at every basic one and then build it up, I'll just pick examples out. So I've got cos to the power of 5 and sine cubed. So which substitution am I going to make? I'll always pull out the lower power to be, it'll end up being the du. So out of the sine cubed, I'll pull the sine x out. Then the sine squared that I'm left with, I've changed to 1 minus cos squared. And then u equals cos x, du is minus sine x dx. Substitute in, and we get a reasonable sort of integral to handle. So subbing that back in, there's my answer, 1/8 cos to the power of 8 minus 1/6 cos to the power of 6. Now, I could have done that by pulling out a cos x, and that would have left me with cos to the power of 4, which I could have rewritten as 1 minus sine squared squared, and use the substitution u equals sine squared. But see, that expansion is going to be bigger. That's why I always pull it out of the lower power, so my expansion is going to be easier to play with. Okay, now that idea is great when they're both odd. So if they're both odd, I can make a choice, but as I say, u will end up being the higher power. In other words, my du, it's the lower power that I'm pulling out. Well, let's look at one where one is even and one is odd. So that one there, I'll pull out of the odd one. So cos cubed, and I was nice to myself there, I made the odd number quite low. So pull out the cos x. The cos squared that I'm left with, I can change to 1 minus sine squared. Do my substitution u equals sine x, and there we go. Add 1 to the power over the power, and we have it. So I always choose the odd one, because by pulling out the cos x, in this case, I'll always be left with cos squared to some power, which I can change to 1 minus sine squared. So when one is odd and one is even, the even will be the u, so that means I'm pulling out of the odd one. So the cos x I'm pulling out to create the du. Well, that just leaves if they're both even. So sine squared, cos squared. I've picked the lowest even numbers that I can for this one. Okay. One of those I will change to the other. I could have just as easily have gone sine squared as 1 minus cos squared. It doesn't really matter. So I've changed my cos squared to 1 minus sine squared. Then I can expand out. And then what I'm left with is simply sine to the power of something. And then I just use the technique for sine to the power of something. And there's my answer. I've sort of cheated because we've already worked out the answer for sine squared, and we've already worked out the answer of sine to the power of 4. So rather than do it all again, I've just substituted straight in what those answers were. But I think you can appreciate the higher the power, the more work that's going to happen, because your expansion is going to have several terms and they will all be sine to the power of something or cos to the power of something. So you can have several different trig functions that you have to deal with. And that tidies up. There we go. An 8th x and then 1 on 32 sine 4x. That one all simplifies. So if both are even, you take a choice which one you want to do. Change the sine squared to 1 minus cos squared, or the cos squared to 1 minus sine squared. Again, I'll probably go with the lower power. In this case, they were both 2, so it didn't matter. But I'll probably go with the lower power to change. So that's sine and cos. Tan to the power of something, or cotan. Again, the technique's exactly the same for both because they're complementary ratios. So I'll just look at the tan ones. So integral of tan x, well, hopefully now we know we'll just jump straight to minus the log of cos or the log of sec. Tan squared, well, tan squared we can rewrite as sec squared minus 1, and both of those we can integrate. Tan cubed, what to do with tan cubed? Well, I'm going to rewrite it as tan x sec squared minus 1. That I can break into 2 integrals. Tan x sec squared, but of course sec squared is the derivative of tan x. And then the other one just becomes minus the integral of tan. So if you don't see derivative times function, then all right, I'll do a substitution, u equals tan x. So du is sec squared. We end up with the integral of u du, and we get half u squared plus the log of cos, which ends up being half a tan squared plus the log of cos. The even one, nice one with these is odd and even are treated exactly the same. So even, again, I just pull out a tan squared. I'm always pulling out a tan squared and turning it into a sec squared minus 1. Because then I can break it up into 2 integrals. One will have the sec squared with it, which is the derivative of tan, and the other just becomes another tan integral, and I deal with that power however we need to. Again, the higher the power, the more work that's going to happen. So tan x, well again, if I do my substitution, u equals tan x, this time I get u squared du, but minus the integral of tan squared, and I've saved a bit of time because we worked out tan squared earlier. I've subbed that answer straight in, and the third u cubed becomes a third tan cubed. So tan, same technique regardless of the power. Pull out a tan squared, change it to a sec squared minus 1, split it into two integrals. Okay, reciprocal ratios then. Well, cotan, as I say, we can do those the same as tan. What about secant or cosecant? I'll look at the secant ones. Integral of sec. Well, if you don't remember what it is, here's how you get it. And I'm sure you'd think of doing that. We'll multiply top and bottom by sec plus tan. Why do that? Well, because then on top, you end up with sec squared plus sec tan, and sec squared's the derivative of tan, and sec tan's the derivative of sec. So you have derivative of a function, log of sec plus tan. Now this usually brings up two questions, and perhaps some of you are thinking of it even as I speak. How would you think of doing that? And probably the first time you see it, you wouldn't. But now you will. Okay? But in reality, as I say, it's one of those ones I try to remember. So, integral of sec, the log of sec plus tan. Log of sec plus tan. So that's the power of 1. Power of 2 is a lot easier, of course. Integral of sec squared, we know is tan. Sec cubed. Sec cubed, I'm going to break up into sec times sec squared. Sec times sec squared. And I'll do a substitution, u equals sec x, which means the u is sec x tan x. dv, yes, in case you haven't worked it out, I'm doing it by parts. dv is sec squared, and v is tan x. So now let's rewrite that one. uv sec x tan x minus the integral of v du sec x times tan squared. Oh, it's a shame those powers weren't the other way around. So what I'll do then is I'll change the tan squared to be sec squared minus 1, creating two integrals. Well, the integral of sec I know. That's log of sec plus tan. Oh, but then this is one of those ones where now I look at it and I don't see it as lines are working out. I see it as an equation. And we're saying the integral of sec cubed is equal to this line here. So I'll move the integral of sec cubed over, and I get two lots of the integral of sec cubed is sec tan plus the log of sec plus tan. Divide both sides by 2, and there we have it. Sec cubed is a half sec tan plus a half the log of sec plus tan. So that's sec cubed. In fact, any time you have an odd power sec, you're going to have to do integration by parts. Because sec to the power of 4 is quite a lot easier. Because sec to the power of 4, I can pull out sec squared, that'll end up being my du, but that'll leave me with sec to an even number, which I can rewrite as sec squared to the power of something. Sec squared is 1 plus tan squared, and I just got to do a substitution, u equals tan x. And so in this one we get 1 plus u squared du, and there it is. So as I say, you're really hoping for an even power. Odd powers, got to do it by parts, got to take a bit of working out. Even, we always pull out a sec squared, that's going to become my du. Leaves me with sec squared to some power. Sec squared I can rewrite as 1 plus tan squared, and then we do a u equals tan x, and we've got it solved. 4G. Let's play with trig integrals.